Last time we talked about the initial value problem in differential equations, just to set up a theoretic framework. This time we're going to talk about the Taylor series method of solutions. Okay. And so in solving a differential equation, we don't actually obtain a function x of t, but what we do is we generate a table of values x0, of pairs t0, x0, t1, x1 up through tn of xn, where we have our approximations of the function. And given this set of ordered pairs, what we can do is we can create a spline which will fit the function. Okay, and thereby having something much more like a polynomial and much easier to compute to get all of the values in between these knots. Now, in order to illustrate how we actually find solutions at those particular points, let's start here with an initial value problem and talk about how we will solve it using Taylor's series. Okay, so here we have x prime is equal to cosine of t minus sine of x plus t squared, and the t is supposed to be t and the x is supposed to be equal to x. I know I do typos sometime, but this is right. And our initial value that x of -1 will be equal to 3. Okay. Now, given this, this is in particular, in general, okay, we can expand x in a Taylor series. We'll have x of t plus h will expand in a Taylor series to be x of t plus h times x prime of t plus h squared over 2 x double prime of t plus x cubed over 6 x triple prime of t plus x to the 4th over 4 factorial, a fourth derivative of x of t, and this can go on all day. We're going to stop it with a fourth order approximation. Now, what we do now is we arrange these. In fact, what I do, I take the derivative by hand. Okay, I will use the product rule at times, etc. We go very carefully, as this is kind of a calculation intensive type thing, calculating the 4 derivatives here. Okay, and when I get down to the 4th derivative, notice that I have a first derivative, second derivative, third derivatives, all as part of that expression. So this will be important. When we create the algorithm, okay, to solve this equation, we will go through and evaluate these derivatives in order. Okay, so we've got the x prime evaluated, and so when we have it evaluated, we can roll it in here. We evaluate the x double prime, and then we can roll it in here and here when we go on down. And so just in general, we do this however many derivatives we choose to take. And then we go back to our Taylor series, and we evaluate it in. Notice that I have it factored out here as to require the minimum number of multiplications. Okay, so this is a pretty tight algorithm, and then the next time around we'll get our next value of t by adding our h to this. Okay, so our h is our difference between the values of t, and we add to it each time going through this loop. And in this way, we get our approximations at the different values. And as I said before, if we want in between those values, we can interpolate with lines or a cubic spline or something like that. And so you get awesome results with this. Okay. Now, the last slide is a special case that if we only do it once, if we only have one derivative from our initial value, and that could be that that's the only information we have, this reduces to what's known as Euler's method, which is a classical way of doing these solutions.